So a few things before getting back to how balls bounce. The first midterm exam is Monday again, in class, essentially 50 minutes. 30 questions, multiple choice, same as has been my standard for a number of years. Again, I encourage you to take the old exams. If you're off grounds to access the old exams, you'll need to re-enter the site in its password-protected mode. I put the password, the username and password on Colab, so you can go look for it. And there's a little reminder saying it should be on Colab. Go find it. Hopefully we're going to be able to see those old questions. Any questions about the exam? I will hold office hours on Monday in the morning rather than the afternoon, so moving them forward. So 9 to 11, I'll be in Alderman Cafe. So if you got questions prior to the exam, come and find me. All right? Oh, and during the exam, I'll try to proofread the exam carefully, but I always, once in a while, I make a mistake. Or I sometimes forget to use words that everybody understands, including non-native speakers of English. Or once in a while, I make a total screw up, like the word taught and the word taught, T-A-U-T as opposed to T-A-U-G-H-T. Is that homonyms? Anyway, if you've got questions about the wording, come and talk to me during the exam. I'll be here. All right? Or any typos. I hope I won't make any typos. Okay, so bouncing balls. The first issue with bouncing balls is essentially why do different balls bounce differently when you bounce them off of a rigid, immovable surface. And why the rigid, immovable surface? And I'm sort of thinking like concrete or steel plate. To look at bounces in their simplest form, don't let the surface get involved in anything interesting. So the rigid, immovable surface, it just doesn't participate except to make the ball bounce. So it's entirely the ball's job. And what's going on there is, if you pick the bouncing ball, it's when you drop a ball just to get it moving so that it can bounce off the floor. One way of doing it is to drop it. Another way to throw it, but dropping it is relatively simple process. If I let go of it, it turns what started as gravitational potential energy into kinetic energy as it descends. So its energy isn't changing, it's just changing forms, right? The gravitational is going down, the kinetic's going up, and just moments before the ball hits the ground, all of its energy, at least according to this story, is in kinetic form, energy of motion. And then when it hits the floor, all that kinetic energy disappears momentarily. There is actually a moment during the bounce, if I drop straight down, when the ball's motionless again. No kinetic energy. Where'd the energy go? It's invested in the ball, and it's been invested by the process of the floor pushing up on the ball, denting its surface. And you have to kind of look, well, you have to look at it from the perspective of the ball, which is a weird perspective, actually. You've got to be careful with it because the ball's accelerating. But the ball's surface is being dented inward. There's a force inward and therefore a force inward, and it moves inward, so there's work done on the surface. To think through this, you have to think of the ball as not a single object, it's multiple objects, it's parts, and there's a denting process. The main thing is that if I dent the surface inward, I push inward, it moves inward, I do work on it, I put energy into it, and that goes on during the bounce. So the energy that disappears out of the ball's kinetic energy and just goes into the ball, I call that the collision energy, the energy that seems to vanish during the impact, during the first half of the bounce as the ball comes to rest. You're okay with the idea that a certain amount of energy just goes into the ball? And we'll name that energy collision energy. The second half of the bounce is the ball rebounding off the surface, pushing its own surface back out, so the ball undents, and that process releases the energy that was stored in the ball, and the ball jumps back off the surface, off the floor. And I'll call the energy that reappears as kinetic energy in the instant after the bounce is over. I'll call that the rebound energy, just to name it. And the rebound energy is always, is never greater than the collision energy. Energy goes into the balls and sort of investment, it comes back out of the ball. You would be pretty surprised if more energy came back out of the ball than went into it. For that to happen, the ball had to contribute some that it had on board already. It has to be like an explosive ball. You drop something that explodes, and yeah, that can happen. But it turned chemical potential energy into kinetic energy along with the rebound. But ordinary balls don't do that. And they don't even manage to turn all of the collision energy back into rebound energy. Only some of it comes back. And with this ball, you can see it's about 70% coming back. How do I know that? Because I'll start with the ball on the floor. I'll invest this much gravitational potential energy into it. One of me height. My height's worth of gravitational potential energy. I'll then let that gravitational potential energy become kinetic, become collision energy, then rebound energy, and it'll come back to a certain height. And the height that it comes back to, which is here, it lost about 30% of its original height. I've gotten back about 70% of the original energy, of the energy that I did on the ball, lifting it to this height. The rebound lifted it to this height. That's only about 70% of the original energy. You okay with that idea, that how I figured out that's about 70%? Any questions about that? And I don't want it to be totally mysterious. Dropping a ball is a good way of measuring how well it gives back the energy in the bounce, because you start from a known height, and you look at what fraction it comes back to in height, and that's the fraction of energy that it returned. Because altitude, the gravitational potential energy is proportional to altitude. Okay, so where'd the missing energy go? It typically becomes thermal energy. A little of it goes off as sound initially. You can hear the ball hit and bounce. It's basically thermal energy. All right, and that thermal energy is real, and I don't think I've ever done it myself, but I watched kids taking balls and bouncing them vigorously on the floor over and over and over and over and over again, as kids are capable of doing, and then measuring the temperature of the ball, and it actually gets hotter. All right, so the thermal energy that's created in this process is real and even measurable. So it's clear that balls don't return all the energy before and after a bounce. And how do you measure that? And why would you want to measure it? It's because in the ball sports in particular, they are so regulated. It's easy enough to spoil an existing sport by allowing technology to come in and change how some of the stuff you use in the sport works. And you can actually sort of ruin the game. Baseball is a classic example. The Major League Baseball is very resistant to changing any of the equipment, because changing the equipment will change how the game plays, and therefore there'll be a before and after with all the record keeping, how many home runs there were, who's the most strikeouts, whatever. You change if suddenly they decided a baseball had to be this big, it would be a very different game, right? So the same is true with the liveliness of a ball. Now, what does liveliness mean? And this is what prompted me to mention that during the exam, if I use a word that doesn't make any sense to you, ask me about it. By liveliness, I mean the extent to which the ball stores collision energy well and returns it as rebound energy. This is a pretty lively ball, meaning that it stores and returns rebound energy very nicely. That's in contrast, to a baseball is a perfectly good example. A baseball is not a lively ball. If I drop it from one of my heights, it doesn't come up to 70%. It comes up to about 25%. It doesn't bounce well at all. And if you substituted for a baseball, you substituted, paint this guy white, make him a little bigger, paint it white and put stitches on it, and pitch this at a Major League Baseball game, it would be a very different game. There would be a lot of pitchers wearing body armor. Too dangerous. All right, there are two classic ways of quantifying the liveliness of a ball, how well it stores collision energy and returns as rebound energy. One way is associated with the energy as it goes in and comes back. The other is associated with the speed as it goes in and comes back. And I'll tell you about both of them because they both show up in the regulation of the sports. The measure that's known as coefficient of restitution, and a baseball I know just offhand, baseballs are regulated by coefficient of restitution. The coefficient of restitution, so I'll use a baseball, compares the speed of a baseball approaching a rigid surface with its speed leaving that rigid surface after the bounce. So it's a speed versus speed. It's a speed over speed ratio. It's the speed rebounding off the surface divided by the speed approaching the surface. And for a baseball, it's got to be about 0.55. So the speed coming back off the surface is a little more than half the speed approaching the surface. If it's significantly above or below that ratio, the ball's not legal for the game of baseball. So it's a ratio of speeds. You okay with that? What's the other possibility? An energy ratio. The rebound energy divided by the collision energy. It's a ratio of a different quantity. And the energy ratio then says how much kinetic energy did the ball have before it hit, how much energy did the ball have after it hit, divide the after by the before, and you'll get a number that will never be greater than 1. And typically it'll be less. Now, those two ratios are different. The coefficient of restitution ratio and the energy ratio, they're different because speed and kinetic energy are not proportional to one another. Kinetic energy is proportional to speed squared. I've talked about that occasionally in class. But it means that if you double the speed of a ball, you quadruple its kinetic energy. The consequence of that not proportionality is that the coefficient of restitution squared is equal to the energy ratio. You have to square the coefficient of restitution because it's a speed ratio. When you square it, now it's an energy ratio. All right? Having said that, then, just to make you think about these things, if a ball's energy ratio is 0.5, so that's the rebound energy divided by the collision energy, and it drops onto a rigid floor, how high will it bounce relative to where it started? You okay with the question? So its energy ratio is 0.5. How many think that it'll bounce to 100% of the height from which you dropped it? How about 50% of the height to which you dropped it? How about a quarter of the height to which you dropped it? Okay, it's going to be it's 50% of the drop height, because about 50% of the energy will come back, and that will allow it to rise, since height is proportional to gravitational potential energy anyway. When the ball turns, there's a brief moment when the energy is kinetic, then stored, then kinetic again, but it'll rise to a certain height, and the height will tell us how much energy came back. So we start from here, and it goes back to about there, about half the energy came back. And so the energy ratio is 0.5. Is that okay? And some number of balls are sort of in that territory. Tennis balls, I think, golf balls, I think they're close to that, about a 0.5 energy ratio. How about the ball's coefficient of restitution, which is a speed ratio, not an energy ratio, is 0.5. So it comes off at half the speed. The rebound speed is half the collision speed. How many think that it'll come back to 100% of the height you dropped it from? How about 50% of the height you dropped it from? How about 25% of the, yes, C it is. It'll come back to about a quarter of its original height. And a baseball is about that, the baseball's coefficient of restitution, as I mentioned before, is a little over 0.5, which means that if you compare the speed when it rebounds to the speed as it approached before hitting, it'll be down by a factor of 2, half the speed. And that means it comes off with only a quarter as much energy, because kinetic energy is proportional to speed squared. So it can only rise to a quarter of its original height. And that's about what a baseball does. Come back, come back. All right? So if you go looking at the regulations for all these sports, you'll find some specification, either in terms of a coefficient of restitution or in terms of a energy ratio describing how the ball has to behave, again, because you'll really change the games if you change those values. You also know that some balls get old and tired. For example, tennis balls. I don't think we ever replace these tennis balls. I mean, they could be older than you guys, and the ball should be livelier than that. It should bounce more than that does. But tennis balls contain compressed air. When they're made, the compressed air gradually diffuses out of the rubber. The air molecules wend their way between the little strands of the molecular strands that are rubber, and they escape. And you know this from getting balloons. You nicely inflated balloon. At night, you leave it in your room. Helium's the worst, because helium is a tiny little atom that sneaks out between the rubber molecules so easily. You come back the next day and the balloon's on the floor looking like a withered old balloon. Okay, so tennis balls lose their balance. Basketballs, we had the other day, we had a basketball in no air. Yeah, Katie. If you square speed, you get energy approximately. There are some factors that go in front of it. You can't literally square the speed and get energy, because a Mini Cooper and a bus traveling the same speed clearly have different energies. Mass is involved there as well. But if you have a ratio of one speed to another, and you have a ratio of kinetic energy to kinetic energy, and they're associated with the same ball, you can simply, the ratios get rid of the other factors that you don't care about. If you're looking at the ratio of a baseball's speed in to a speed out, and the ratio of baseball's kinetic energy in to kinetic energy out, that ratio gets rid of the issues like what is its mass and any other factor. So now you can say, now I can actually say that if you square the speed ratio, you'll get the energy ratio exactly. All the other factors cancel. Is that okay? All right. Okay, so this is the extent to which a ball bounces. Do I have just for fun, two bouncy balls or seemingly bouncy balls? You have to be able to see the floor. So this is it's pretty much a bouncy ball, not super good. How about this guy? So people have managed to engineer. These guys feel very similar. You'd have a tough time telling them apart by feel. I can tell them apart. Well, this one's got a smiley face on it. They're known to the official names are happy ball, unhappy ball. I don't know why. So this one's as dead. And people have engineered developed the deadest rubbers imaginable. They serve purposes. We'll talk about things like shock absorbers. The shock absorbers on your car, it turns out, are not to make the impacts when you drive over a curb, for example, more comfortable. They don't absorb that shock. That's not the issue. What they're doing is they're wasting energy as efficiently as possible so you don't bounce down the road after driving over a curb. The car sits on springs, and we've seen what happens when you have an object oscillating on a spring. It oscillates up and down until it gets rid of its excess energy. So shock absorber's job is to get rid of the excess energy. We'll deal with that in the future in more detail. But materials like this that are incredibly dead, like this guy. And again, dead is is my name for, and I'm not unique, I'm calling it dead, for things that bounce very poorly, that waste almost all of the collision energy and have little or nothing left as rebound energy. Having really dead materials are useful for certain purposes. Another thing that's like that's incredibly dead, is a beanbag, no bounce. So they're useful. All right, that's the story for the balls themselves. So when you bounce them off of rigid immovable surfaces, the rigid immovable surface is just uninteresting. You don't care about any of its characteristics. The ball is completely responsible for storing collision energy, returning it as rebound energy, and so on. What about if the surface isn't completely rigid, still immovable? Let's not let it go anywhere, but let's allow it to dent during the impact. Well, if a ball hits a surface that dents during the impact, then two surfaces are having work done on them and storing energy. The ball is having work done on it, and again, it takes up the frame of reference from which you watch the work being done is a little messy, but you can still imagine that the surface of this formerly spherical ball now has a flat spot that's getting shoved deeper and deeper into it. So there's a force inward, it's moving inward, work's being done on it. But what about the surface? The surface started as this lovely flat surface, at least in my vision of it, and now something's smushing it inward and it's moving inward. So it's being dented and it's having work done on it too. Can you picture that? And they're sharing the collision energy. The ball and the surface from which the ball is bouncing, they're sharing the collision energy. And who gets more? Well, since they're pushing on each other equally hard in opposite directions, that's Newton's third law after all, the amount of energy that's invested in their surfaces is related directly, is proportional to how far the surface is dented. So if the ball and the surface both dent the same distance, a centimeter, say, during the impact, they both get the same amount of energy stored in them, or at least invested in them. So if the surface only dents 2% as far as the ball dents, then the surface gets 2% of the energy, the ball gets the 98%. I should be careful, is it 2 and 9? There might be a factor of 2 that I'm missing here, but you can imagine that if they dent the same distance, they get the same energy. If one dents a little bit and the other dents a lot, the one that does a lot of denting gets a lot of the energy. All right? Actually, the 2% comes to mind because, again, in the game of baseball, during the ball-bat collision, where the bat is made out of wood, the bat dents about 2% as much as the ball dents. So it gets about 2% of the collision energy, the ball gets the rest. All right? And now the question comes about who stores energy well. Well, if they both store energy equally well, then who cared who did the denting? They both return, 50% of the energy comes back fine. The rebound's sort of a 50% energy return rebound. But if there's a big difference between the ball's ability to store energy and the surface's ability to store energy, then you can get some strange rebounding effects. For example, I already showed you a beanbag is terrible at storing and returning energy. When it dents during an impact with a hard, rigid surface, the energy is invested in it, and it turns it all into thermal energy by friction between the beans. And then it's gone. Nothing comes back out. This guy doesn't bounce at all. So, terrible bouncer. But what if you let it bounce off a surface that is very lively itself, that is a surface that stores energy well and returns it well, and that is also soft enough that it dents significantly during the impact. So it gets a good dose, a good share of the collision energy. Like a trampoline. So, this is poor man's trampoline here. This is a lively surface that's pretty soft. So if you push on it, it dents, and when you let go, it rebounds nicely. So it's good at storing and returning energy, and it's soft. In fact, it's sort of soft on the same level as the beanbag. In that case, the beanbag bounces. Who's doing the bounce? Well, they're both sharing the impact, the collision energy, The beanbag is just squandering its portion, gone. But the little trampoline bag is getting about half the collision energy, storing it nicely, and returning it nicely. And the beanbag bounces, not because the beanbag's bouncing, but because it bounced off, it went off a lively surface. So this, examples of this are like a trampoline that kids will play on. People's coefficient of restitution is pretty close to 0. We don't bounce. You drop us on the floor and we flop, okay? So having us bounce on hard surfaces is a really bad idea. But if you drop us on surfaces that are, first off, very, very lively themselves, store energy nicely, and second, are soft compared to us, so they do a lot of denting compared to us. So you drop somebody on a trampoline, it dents deeply, it gets most of the collision energy, and stores it nicely and returns it nicely. And the bouncing process then gives you a nice rebound. The fact that people bounce off trampolines doesn't say that the person is lively. It says that there's pairing. The person and the trampoline together as a team is a lively structure that gives you a lot of energy return. Okay? The opposite of this, I can take, and I did this last time, I can take the liveliest ball I have up here, which is the pink one, and this bouncing off of a hard surface bounces beautifully because the ball gets it gets all the collision energy for practical purposes, stores it nicely, returns it nicely, and rebounds beautifully. But if you drop it on a surface that is again soft, sort of relative to the ball, so that the surface gets a lot of that collision energy, and a surface that not only is soft, but is also dead, does not store energy well. So if you drop the ball off of a beanbag surface, the ball won't bounce well. And sand is a good example. Actually, dry sand. Why dry sand? Because wet sand is much harder. It doesn't store energy well either. But because it's harder, the sharing of energy isn't quite as overwhelmingly into the sand. When you drop a ball on wet sand, the ball dents some because the sand doesn't dent very far. The ball has to do some of the denting, and it does some of the energy storing. It can rebound, but on dry sand, essentially no rebound. The sand got all the collision energy and wasted all of it. Questions about this stuff either? Okay. An example where sand, even dry sand, can allow a ball to bounce. A beach ball. A beach ball is so soft that it's softer even than the dry sand. So when you drop a beach ball onto dry sand, they both dent some. The sand dents, wastes all the energy it gets as a result. But the beach ball also dents and stores the energy pretty well and then can rebound. So it's always you have to compare which surface does most of the denting, how dead is that surface, or how lively is that surface, the one that gets the energy. Okay? So I've now walked through ball bouncing off a rigid surface where it's entirely the ball's job. A ball bouncing off a surface that can bend. And now they're sharing energy and sharing the job of doing the rebounding. What if we allow the surface to move? So the question I've got for this is, how does a moving bat drive a ball forward? And I'll come to the details of that in a minute. But you can see if I take a surface that's motionless and bounce the ball off it, I get the usual bounce. A surface is motionless, and to make it life simple, I'll let the surface let the surface be pretty rigid, so it isn't so involved in the storing and returning of energy, but its velocity does matter. If I drop the ball off that surface while the surface is motionless, we're back to normal, the first story. It's the same as if I dropped it off the floor. But if I bounce the ball off the surface while the surface is rising, the bounce is quite different. Because now the ball bouncing off a surface that's moving, the mechanics of the ball hitting and storing energy and then rebounding and returning energy is complicated by the fact that the surface is moving and the speeds of approach and the speeds of separation are complicated now because you're bouncing off. The speed, actually the velocity of the surface matters all of a sudden. I did one where you end up with the ball going, hey, thanks, going faster. You can also do the reverse. You can kill the balance by dropping off of a descending surface. So, come back. You get to watch me fumble around with the ball. Good physics in that, not really. The way I'll try to convey the understanding of what happens when a ball bounces off a moving surface is to walk you through the same story that's in the book, but it's the story of a ball hitting a moving bat, as in the game of baseball. But if baseball doesn't thrill you, it's the same story of a ball coming in, a soccer ball coming in and bouncing off your forward moving leg. The character's changed. It's a bigger ball, softer ball now that being a soccer ball. And instead of a wooden bat, it's your leg, but otherwise identical. And so to work our way through this, first, some questions. And the question I have here is that when two cars are they're traveling along, and their speeds are 60 miles an hour for one car and 50 miles an hour for the other car. Just speeds as viewed by a pedestrian who just is standing there watching. Oh, that car is going 50 miles an hour, and that car is going 60 miles an hour. Suppose they hit each other. Their collision speed, that is the speed with which the two cars approach one another, which is equivalent to sit in one of the cars, watch the other car come at you. How fast is it traveling? What is their collision speed, or what is the range of possible collision speeds that can be achieved with two cars, one traveling 50 miles an hour, one traveling 60 miles an hour? And you'll notice I said speeds, not velocities, because I have not pinned down velocities. You okay with the question? Talk it to death. A, how many think that it's 110 miles an hour, specifically? Okay, how about between 50 miles an hour and 60 miles an hour? How about between 10 miles an hour and 110 miles an hour? Okay, and finally, between 0 miles an hour and 60 miles an hour. Okay, there's the plurality is C, is the 10 miles an hour to 110, but there's substantial voting for A and B as well. And the answer actually is C, between 10 miles an hour and 110 miles an hour, which is sort of why I asked the question. Because the fact that the two cars are traveling 50 miles an hour, 60 miles an hour, I didn't tell you which way they were heading. And the extreme so any direction of travel is possible. And the two extremes that we need to pay attention to are, suppose they're both heading toward each other. If they're doing that, so this one's going, according to the pedestrian standing there watching, this one's going 60, that one's going 50, they're approaching each other. The distance between them is shrinking by 110 miles per hour. If you're in one watching the other one come at you, it's, wow, this is a head-on collision, really fast, 110 miles an hour. Everybody okay with that idea? But there's another possibility. They're going the same direction. And one's going 50 miles an hour, say, to your left, and the other one's going 60 miles an hour to your left. The 60 mile an hour one is gradually overtaking the 50 mile an hour one, and if they collide, it's a fender bender. It's a 10 mile an hour approach. From the car in front traveling 50 miles an hour, they look back and go, that car's coming at us, slowly creeping up on us, 10 mile an hour collision. Is that okay? So with cars traveling at these two speeds, you can get everything between 10 miles an hour, the fender bender, and 110 miles an hour front head-on collision. Big difference in speeds. So there's a range of a factor of 11 in potential speeds, in possible speeds. Actually, potential's it's a loaded word, but possible's not. Okay, so factor of 11 in speed. Remember that speed and energy is often related, well, it is related to speed, the square of speed. So the second question is this one. Two cars are traveling, again, 60 miles an hour and 50 miles an hour, surprise. And the difference now is what's the range of possible collision energies? That is the energy invested in the bounce when the two of them bump. How does that vary? You okay with the question? And my little hint about kinetic energy is proportional to the square of speed. What range of possible collision energies is available to us? A factor of 5/6, a factor of 6/5, a factor of 10, a factor of 121. Ooh, not many voters. I was hoping for a huge turnout at 121, which might be the right answer. 121, anybody? Yeah, it's the right answer. There's a huge factor in energy available in these two in this range of collisions. So here's the story. If the 50 mile an hour car is overtaken by the 60 mile per hour car and they hit, and the speed of their approach, that is the speed with which one is approached by the other, is 10 miles an hour. So the energy is going to be related, the kinetic energy invested in that collision is going to be related to, or proportional to, 10 miles an hour squared. And there are other factors that we won't worry about right now, because again, we're doing a comparison that is ultimately a ratio, and all the factors will cancel out. On the other hand, if they do a head-on collision, they're approaching one another 110 miles an hour, much faster, 11 times greater speed of approach. You okay with the fact that it's a factor of 11? The energy goes as the square of the speed. So it's 121 times. The proportionality now is 121 times larger than the one for the overtaking fender bender. So the public service announcement component of this little observation of the story is, a head-on collision between two cars traveling almost the same speeds is like 100 times more energy is sort of invested into the collision than when they're traveling the same direction and bump at highway speeds. This is why when you're driving down the road on a two-lane road, people in front of you, people coming at you, and you're suddenly faced, heaven forbid, this ever happened, but you're faced with a choice between hitting the car in front of you, traveling your direction, and hitting the car on the other lane, heading the opposite direction. There is no comparison between the trouble that will ensue in these two collisions. Don't hit the oncoming car. The energy of the collision is so much greater, a factor of 100. That energy is going to go do stuff. You don't want that energy anywhere near you. The highway collision fender benders where you hit the car in front of you, now you guys have to worry that you don't do something stupid like drive into the oncoming traffic or off the road. I mean, I wouldn't say stupid, but unpleasant. But otherwise, it's no big deal. Collisions happen like this all the time where cars traveling at highway speeds bump into each other at an approach speed of 3 miles an hour, and you don't even see any damage. I mean, the cars actually just take it and keep on going. All right? That would not happen in a head-on collision at highway speeds because the energy invested in the collision is so horrendous. The cars are designed to try to squander this energy of collision as efficiently and effectively as possible and keep it away from you. So they crumple in various ways. They actually have work done on their parts as they crumple, and they try to turn the energy into thermal energy, but still, skip it. All right. So when two moving objects, the back out of public service announcement into we're hitting a baseball with a baseball bat. When the bat and the ball are heading toward each other and are approaching for a head-on collision, there's a lot of energy available here. The approach speed is huge, and the energy investment can be huge. All right, so it's a three-part story, and just for this purpose, let me unhook the baseball bat. We'll come back to the bat, the hanging bat. So the baseball bat and the ball, and the way I've got it drawn up there, the baseball bat swung by a batter is moving toward the pitcher and the outfield. The baseball thrown by the pitcher is heading towards home plate. They are both moving objects as viewed by you guys in the stands. So you're there cheering on your favorite player. I don't know whether it's the pitcher or the hitter. Take your pick. And just for simplicity, we'll say the bat's moving toward the pitcher at 100 kilometers per hour, just to be metric, sort of. The hour is a weird unit. Okay, the baseball, having been pitched, is heading towards the catcher or the batter at 100 kilometers per hour. What is the approach speed of the two objects? How fast are they heading toward each other? Got your head? It's 200 kilometers an hour, right? You all comfortable with that idea? All right. And it actually says there, ha ha. Can you read? Yes. Okay. So now let's leave the perspective of people in the stands, and let's envision yourself as a bug, your favorite bug, sitting on the bat. So now you're on the bat. I drew it. I forget which way I drew it. Okay, you're sitting on the bat, heading wherever it's heading, and the ball's coming at you at 200 kilometers an hour because you're moving with the bat. You all okay with that idea? The ball comes in and it bounces off the bat. And for simplicity, we're gonna use a wooden bat and a big massive bat like Babe Ruth would have swung. And then what's nice about all this is the bat basically is like a rigid, immovable object. It just is not going to do anything interesting. The ball is going to bounce off of it. That's the point. Let's keep the bat simple. Boom. And remember, the baseball has a coefficient of restitution of about 0.55, which means that if it comes in at 200 kilometers an hour, approaches the bat at that speed, it's going to go out at 0.55 times that speed, which is 110 kilometers an hour. So from the bat's perspective and us living on the bat, the ball's going to come in at 200 and go out at 110. Everybody all right with that idea? Now let's go back to your perspective as fans sitting there in the crowd. And the bug's perspective, that the ball is heading towards the outfield 110 kilometers per hour, translates into, now from the perspective of you and you fans out there, as whatever the bat's doing, the ball is outrunning it towards the outfield by an amount of 110 kilometers per hour. But the bat itself, as I set it up in the original story, was heading towards the pitcher in the outfield itself at 100 kilometers an hour. And the ball is outrunning it by 110. So you have to add those two velocities. The velocity of the bat is already 100 kilometers per hour toward the outfield. The ball is going 110 kilometers per hour toward the outfield faster than the bat. So add the two. So when you add them, you get 210 kilometers per hour. The ball, as viewed by the fans in the stands, is heading toward the outfield at 210 kilometers per hour. Questions about that idea? Well, 210 kilometers an hour, where'd that come from? It's a huge number. The story up until this point only had things like 100 kilometers an hour. Where did we get this huge number? It's because the ball bounced off of a moving surface. And it went from approaching that moving surface really fast to going with that moving surface medium fast. Yeah, that doesn't make sense. But when the ball bounces off a surface that's approaching the ball, the rebound ends up outrunning the moving surface. I'm not adding value to this discussion. For perspective, these two original speeds, 100 kilometers an hour for a bat is pretty easy to achieve. 100 kilometers per hour is like probably middle school or a high school fastball. It's not a very big fastball, not a very big swing. And yet, the ball bounces out of there, traveling 210 kilometers an hour, which is 130 miles an hour, 140 miles an hour. Really fast. This is why a ball that has been thrown and then hit hard is the fastest thing in the game. It's going very fast. Anything else I wanted to add to this? Can you follow the story? I mean, I know I kind of got muddled it up toward the end. What else did I want to say with this? The bat. The baseball itself is already not a very lively ball, right? I told you that it only comes off at about 0.55 of its incoming speed. You can see if it were a wonderfully lively ball, like my pink ball or better, this arrangement where the ball rebounds, it would, instead of rebounding at 110 kilometers per hour faster than the bat, it might come off at 200 kilometers per hour faster than the bat. And then when you go back to the stands, the perspective of the fans in the stands, it would be outrunning the bat by 200 kilometers an hour. You'd have a 300 kilometer outgoing ball, 300 kilometer per hour outgoing ball, way too fast for anybody to deal with. So keeping the ball relatively dead turns out to be quite important. The other thing that's quite important is to either have the bat be very rigid or not lively. You do not want a bat that bends nicely, stores energy well, and then returns the energy well. That being an aluminum bat. So aluminum bats, because people can engineer them like crazy ways, become trampolines for a baseball. So in contrast to a wooden bat where there's not much you can do, the bat's so hard that it doesn't participate much in the bounce. An aluminum bat can participate in the bounce. And it can take the fact the ball is dead becomes unimportant if the bat is very nice and flexible and plays trampoline. Because then the ball doesn't get all of the collision energy. A lot of the collision energy goes into the bat, which flexes nicely, stores energy nicely, and then flings the ball back out at ferocious separating speed. So aluminum bats result in much faster outgoing baseballs, and consequently are much more. They change the game. They make it so that the pitchers need to be wearing body armor again. Is that okay? Last tidbit to talk about with bats, and I'll just do it. The bat is not a completely rigid object. I started showing you this last time when I was looking for a musical instrument and focused on the bat. Bats are not perfectly rigid, they can flex. And the type of flexure that is most important in a bat, and this applies to other sports equipment as well, they're not all perfectly rigid, they flex. A hockey stick is a great example. The flexure that matters in a baseball bat is sort of the flapping wing behavior, where the middle moves one way and the ends go the other. What I'm doing here is I'm bending this stick first this direction, middle down, wings high. Then it's middle high, wings down, back and forth. This is the motion of the little Fisher-Price xylophone tines. When you smack them, you get this motion, this flapping motion in the tine. And it's a spring-like object taken away from equilibrium, and it goes back and forth about equilibrium. That whole story, it's all there. And there are two places that don't move significantly if I did this right, and that's where they support the flapping motion in Fisher-Price. Well, with a baseball bat, the flapping motion's there. It's a little messed up by the fact that the wood is not uniform thickness. It varies. But this, with the red mark, is one of those special spots that doesn't move. It would be where you would support the xylophone tine if it were a xylophone tine. There's one here and there's one somewhere up here. And when the baseball hits the baseball bat anywhere but right at that red line, it makes the baseball bat begin flapping. And you hear the sound, and that was the sound I was playing for you last time. Bum, 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 bum. Bum, 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 bum. It's not me, it's it, right? Okay. But if you hit it right there at that special spot where you would normally support the xylophone tine, and which doesn't move during the flapping process, it also doesn't cause the flapping process. There's no bzz, bzz, bzz. So this is a sweet spot. It's called the vibrational node. And when the baseball hits that spot on the baseball bat, which is what the batter wants, there's no buzz, and there's no investment of energy into the buzz. So the ball bounces better, and you get a farther hit with the ball. So that's the story of bouncing balls to a reasonably good extent. And see you on Monday for the exam.